welcome back to my channel. I hope you're doing well. This is episode number 2 of the glaciation series, and today we're going to be focusing on climate change and glaciation. If you're new around here, hi, I'm Lara. You're so welcome. This is part of the A-level geography revision series. We're still on inquiry question 1, which is how has climate change influenced the formation of glaciated landscapes over time? If you're new here, please subscribe down below. I make these videos every week on a Monday. I also upload on a Thursday at 4:30 and a Saturday at 10 o'clock in the morning. So without further ado, let's get into it. How has climate change influenced the formation of glaciated landscapes? You may ask. You may not, but you may ask. So what is the evidence? Long-term climate change. The 3,200 metre East Antarctic ice core records the last 800,000 years, especially the bubbles of concentration of CO2, while the ice contains oxygen isotopes. This tells us about the history of glacials and interglacial periods before the last one. Medium-term climate change. This is based on the changes in vegetation, such as wood from the Ogwen Valley. This is known as dendrochronology. We also study pollen sequences. We can tell this through some relative changes and some absolute dating techniques. Dating as in time periods rather than romantic dating, obviously. And then there's short-term or recent climate change. This is studied through multi-international corporations such as the Intergovernmental Panel on Climate Change. These look at the scientific researches that's going on right now. So throwing it back to the Pleistocene, geological time is split into eras, such as the Cenozoic era, periods such as the Quaternary period, and epochs such as the Pleistocene or Holocene. The Quaternary period started about 2 million years ago. The Pleistocene epoch within that lasted about 2 million years and ended 11,700 years ago. Roughly every 200 to 250 million years in the Earth's history, there have been major periods of ice activity. Most recent and significant occurred during the Pleistocene epoch of the Quaternary period. This has led to cold periods known as glacials and warm periods known as interglacials. In the last 1 million years, there has been as many as 10 glacial periods separated by interglacials. During the glacial periods, the climate cooled sufficiently for precipitation to fall in the form of snow rather than rain. This resulted in the growth and formation of huge ice masses, which in the northern hemisphere spread south over large parts of Europe, Asia and North America. During the warmer interglacial periods, some of which were considerably warmer than the conditions we experience today, much of the ice melted and the ice sheets and glaciers retreated. The characteristics of the Pleistocene. There wasn't a single ice age in the approximate 2 million years that it lasted. Temperatures fluctuated enough to allow ice to advance and retreat. The extent of the ice during each glacial was different. There were also fluctuations within each major glacial. They're relatively short-lived pulses of ice advances known as stadials, and the warmer periods of retreat known as interstadials. The most recent stadial in the British Isles was the Loch Lomond stadial, which was completed in about 1,000 years. It is possible to come up with 2 main conclusions from these characteristics. Number 1, medium and large-scale glacial erosion occurred, such as those found in the Alps, are likely to be the result of several glacial advances. Number 2, the depositional features tended to be the result of conditions and processes at work during the most recent glacial interglacial cycle. There are 4 main types of Paleoclimate proxy data. This is how we collect data about the past and the climate in the past. Biological, these include things like tree rings, pollen, corals and fossils of plants, animals, insects, microscopic creatures such as diatoms. There's also cryological. Such examples are cylindrical columns called ice cores. These are collected by drilling through dense, deep ice sheets to find trapped air bubbles and trapped dust. The third one is geological proxy data, such as these can be found in sand dunes, ocean sediment, glacial debris, stalagmites, also volcanic rocks and the Earth's geomagnetic field, as we touched upon in one of the videos in the tectonic series. If you want to know more about paleomagnetism, I'll link a video up here for you and you can have a look at what that's all about. They can also be found in ocean sediments for historical, such as the written records of atmospheric changes and biological events, like timings of spring blooms for a tree or how far north an insect is moving, for example. So there was a little ice age in 1550 to 1850. This brought cold winters, crop practices adopted to be shorter, villages were completely destroyed due to the advancement of glaciers, and the sea ice extended out from Iceland for miles. What caused this? So increased volcanic activity, which when that occurs and there's a load of gas in the air or kind of ash in the air, the sun can't get in to penetrate and warm up the earth, so the earth temperature decreases. Obviously this kind of depends on the scale of the volcanic eruption, but that is generally what it's due to. As well as solar radiation. This occurred in the Holocene, and it had come after a period known as the medieval warming period. So following the general fluctuations of the Earth's atmosphere, this kind of was expected, but also that's up for debate. And then there was also increased insulation coming from shortwave radiation, so it just radiated out of the atmosphere again. It didn't stay trapped in and warm up the planet. What factors actually influence whether an ice age can happen? The primary driver is the climate. Changes in the Earth's orbit around the sun from a circular pattern to an elliptical pattern. This change is known as the Milankovitch Cycles, which we're going to talk about in a minute. That is the primary driver in whether an ice age can happen. But on a shorter time scale, changes in solar output creating flares, which can increase the temperature, known as solar cycles. So this can not create an ice age, but it can stop it from happening if there is this solar flare. It can also be affected by plate tectonics, volcanic eruptions, and the oceanic circulation known as El Nino or La Nina, which we're going to talk about in a few weeks' time. Also, the enhanced greenhouse effect. Milutin Milankovitch was a mathematician and an astronomer. Between 1912 and 1941, he carried out calculations that showed the Earth's position in space, its tilt, and its orbit around the sun. They all change. These changes, he claimed, affected the amount of incoming solar radiation, where it falls on the Earth's surface. They also produce three main cycles of 100,000 years, 41,000 years, and 21,000 years. These cycles will be sufficient to start an ice age, or end one. These are known as the Milankovitch Cycles. So the first Milankovitch cycle we're going to talk about is known as the Eccentricity Cycle. The path of the Earth's orbit around the sun is not a perfect circle, but an ellipse. The elliptical shape changes from less elliptical from a near perfect circle to more elliptical and back again. This is due to the gravitational field of neighbouring planets, particularly the larger ones such as Jupiter and Saturn. The measure of the shape's deviation, being from a circle to an elliptical, is known as eccentricity. That is, the larger the eccentricity, the greater its deviation from a circle. Thus, in terms of eccentricity, the Earth's orbit undergoes a cyclical change, from less eccentric to more eccentric and back. One complete cycle of this variation lasts 100,000 years. The second one we're going to talk about is the axial tilt. So as you may know, the Earth sits on an axis of about 23.5 degrees. We all know that the Earth's spinning around its own axis. This is the reason we have a day and a night. However, the axis is not upright. Rather, it tilts at an angle between 22.1 degrees and 24.5 degrees and back. These angles are measured between the angle of the axis to an imaginary line, normal perpendicular, to the Earth's plane of orbit. A complete cycle for the axial tilt lasts about 41,000 years. Greater tilt means the hemispheres are closer to the sun. For example, during summer, they will experience a larger amount of heat than when the tilt is less. In other words, regions in the extreme upper and lower hemisphere will experience the hottest summers and the coldest winters during the maximum tilt. And then the third one, precession. Aside from the tilt, the axis also wobbles like a top. A complete wobble cycle is more or less 21,000 years. This motion is caused by tidal forces from the sun and the moon. Precession as well as tilting are the reasons why regions near the poles experience very long nights and very long days at certain times of the year. For example, in Norway, the sun never completely descends beneath the horizon between late May to late July. The Milankovitch cycles are among the current argument fielded by detractors of global warming concepts. According to them, the Earth's current warming is just part of a cyclical event that will take thousands of years to complete and cannot be prevented. How does this change the temperature? Eccentricity affects the amount of solar radiation the Earth receives, and therefore altering the global temperature. The obliquity cycle, or the tilt cycle, and the equinoxes, the wobble cycle, both affect the seasons, hence affecting the global temperature. So we're going to touch on some other things that can also affect the temperature of the Earth now. Number 1, solar variations. The solar cycle, or solar magnetic activity, is the near-periodic 11-year change in the sun's activity, including changes in the level of solar radiation and ejection of solar material, and appearances, such as changes in the number and size of sunspots, flares, and other manifestations. Changes occurring in the sun itself can affect the intensity of the sunlight that reaches the Earth's surface. The intensity of the sunlight can cause either warming during periods of strong solar intensity or cooling during periods of weaker solar intensity. The sun follows a natural 11-year cycle of small ups and downs in intensity, but the effect on the Earth's climate is relatively small. Number 2, volcanic eruptions. A volcanic eruption occurs when hot materials are thrown out of a volcano. Lava, rocks, dust and gas compounds are some of these ejecta. Eruptions can come from side branches or from the top of a volcano. Some eruptions have terrible explosions that throw out large amounts of rocks and volcanic ash that kill many people. Some are quiet outflows of hot lava. Several more complex types of volcanic eruptions have been described by volcanologists. These are often named after famous volcanoes where that type of eruption has been seen. Some volcanoes show only one type of eruption during a period of activity, while others show a range of types in a series. When volcanoes erupt, they emit a mixture of gases and particles into the air. Some of them, such as ash and sulfur dioxide, have a cooling effect because they are, or the substances they cause, reflect sunlight away from the Earth. Others, such as CO2, cause a warming by adding to the greenhouse effect. Volcanic eruptions do not follow any specific pattern of eruption. They can erupt at any time and are really difficult to predict. And then finally, meteorological processes. Meteorological processes are those that take place in the Earth's atmosphere. The lower part of the atmosphere, the troposphere, with thickness from 18 kilometers to 8 kilometers at the poles, is of primary importance. Essentially, the sole energy source for different meteorological processes is solar radiation. The existence of climatic zones and formation of different situations that determine weather conditions are caused by an uneven influx of solar energy to the Earth's surface. The non-uniformity of radiation conditions is largely due to astronomical factors, such as the variations of the sun's luminosity, variations of the Earth's orbit elements, and other parameters, and the local physiogeographical conditions, such as orography, the distribution of land and sea, the relief of underlying surfaces, and other conditions. This is constantly occurring in the troposphere. That is episode number 2 of the glaciation series complete. I hope you learnt something. I'm sorry this was such a long one, but I just wanted to get it all into one video, so if you don't understand this, at least it's all in one place for you. You can go back, rewatch it. I'll leave a few timestamps in the description if you missed a few things and want to go back. And yeah, I hope you enjoyed. I hope you learned something. Please subscribe down below. I really want to get to 1,000 subscribers by the end of the year, just so that more people can see my stuff, more people can learn about geography. If you're a geography teacher, please share this with your class if you found it somewhat useful. If not, please leave me some constructive criticism down below. I would actually quite like to hear it. But yeah, I will see you in my next video. Same time, same place next Monday, guys. Bye.